Hello. Last time we introduced the concepts of position and displacement and velocity, average velocity, sorry, and we used a cart moving side to side to help us illustrate those ideas. And these were in the context of one-dimensional motion. So we're going to continue with that example, really unwinding it until we're really good experts at it. And we're going to, in this video, we're going to focus on constructing position versus time graphs and interpreting those and seeing what they mean. So I just want to remind you, if the average velocity was positive, that meant that the change in displacement over some amount of time was positive. There's a change in position, so the displacement over some amount of time was positive. So that means that, basically means it was, on the whole, moving to the right. If the displacement was negative, then on the whole, it was moving to the left during that time interval. And the formula for average velocity was the displacement divided by time, or the change in position divided by the change in time, over the interval that we are interested in. Okay, so those are things we saw. Those are terms we came up with. What I want to do is set up a situation. So let's imagine the cart starts, well, let's say it starts at 0, as I did before, and it's going to move to the right. And let's say, I don't know, every second it moves a few centimeters, in a steady way. So it goes 1, 2, 3, 4, 5, 6. Hopefully it's pretty steady. Okay, so I'm going to push it, and you can imagine that this could be a car going down a road or something. Easy, right? So, as long as you have a camera ready, you take out your phone, take a video, you've got a good, you have characterized that event in the world, and you've stored it, and you've got it. So you can describe what happens to anyone. However, for us, we want to do more than just have like a literal one-to-one movie of something. What we actually want to do is turn that motion into a graphical object that we can analyze using all the tricks that you have learned in math classes. So that's the purpose of today's activity. So we're going to imagine here that we have a motion, and let's say it starts, I may kind of fudge the numbers so they come out to be nice round numbers. But let's say that at time 0, it's at 0. At time 1, it's at 0.2 meters. At time 2, it's at 0.4 meters. At time 3, it's at 0.6 meters. Okay, you can imagine such a thing. I can do it, but that's the idea. Okay, so at 0, it was at 0 meters. At time 1 second, it was at 0.2 meters. At 2 seconds, it was 0.4 meters. And at 3 seconds, it was 0.6 meters. From that information, we can construct a graph. And by convention, physicists like to put time on the horizontal axis and position on the vertical axis. And the reason is we think about the positions of things as somehow being determined by time. We don't normally think of it as position controlling time. We think of time as controlling position. But you guys know how to do math. You can always invert relationships. Okay, so to do that, what I would do is I would just plot points in that situation. Okay, and the times would be 0 seconds, and then I would have 1 second, 2 seconds, 3 seconds, and then remember what numbers I threw out at you. I said 0.2 meters, 0.4 meters, and I said 0.6 meters. Okay, and those are the the points that the kind of values of position that I indicated. So over here, for labeling things, this is going to have position. So I'll just put an X there because we're moving in the X direction. Right at the end of the video. And over here, we're going to put time, T. Okay. Very good. Now, to have a really nice graph, you should label the units for everything. Sometimes throughout the semester, after we get used to it, probably, even though I shouldn't, I will forget and drop my labels. But if I'm measuring position, by default, I mean meters. If I'm measuring time, I'm by default seconds. Okay. And then to get my graph, it's just like in math class, I would plot points. So at time 0, the position was 0. Hopefully that's visible. I'm struggling with my marker there. At time 1, the position was 2. At time 2 seconds, the position was 0.4. And at time 3 seconds, the position was 0.6. Okay? And if we made more measurements, we could fill it in. I'm going to assume that it was just steady all the way in between. So I would have a graph kind of like that. And if this was experimental data, you're really not supposed to fill in points that you didn't measure, because you can't assert that you know things that you didn't actually measure. But let's assume that we measured all these points in between. Very good. And that produces a nice straight line, to my eye, within the limits of my artistic abilities. All right. Now, so we've got a representation of position versus time. Now, last time we mentioned another quantity. We also had average velocity. So the formula for average velocity that we had before was the change in position, or the displacement, over the change in time. Now, to apply this formula, you really need to talk about which time interval. And when you do sapling problems, to read the problem carefully. On some of these, it'll say specifically, is it for the first time step, the second time step, the whole time interval, and the average velocity is not well defined until you say it over what interval. In this case, let's apply this formula over the entire 3 seconds. So from time 0 all the way to 3 seconds. So to apply this, first let's just do it, okay? So change in position, so that'd be final position minus initial position. Well, the final position, now I have a graph so I can refer back to that. That was at 0.6 meters. The initial position was at 0 meters. So the change in position is 0.6 minus 0. So this would be 0.6 meters minus 0 meters divided by the change in time. And I'm doing the whole interval. So that means final time minus initial time, 3 seconds minus 0 seconds. And the answer I get is 0.2 meters per second. So that's kind of a curiosity. My velocity is 0.2, my average velocity is 0.2 meters per second. Now, that's kind of interesting. And all this thinking about math class kind of makes me think about change in something over change in something. And I think about then, what does that mean on a graph? And then I realize, the average velocity is in fact the slope of this line. More precisely, it would be the slope of the secant line, which goes from between the points indicated by our interval, in this case from 0 to 3. So what you could do then is draw a line which connects initial and final points. Well, in this case, that just is a line which lies right on top of the blue line. But in a minute, we'll do another example. And we learn, and then what I would say is the slope of the secant line gives the average velocity. Okay, so that's the line from starting point to ending point. Draw a straight line, regardless of what happens in the middle. And the slope of that line would be the average velocity on that interval. So slope of a position versus time graph is going to be associated with velocity. Remember that. Kind of sear that into your brain. We're going to use that over and over. The slope of a position and time graph is related to velocity. This was pretty easy because the motion was nice and steady. Let's do another situation. Let's do a situation where the velocity is not so steady. The motion is not so steady. Okay? So what we're going to imagine is a situation where we start at 0. Actually, no. Let's imagine a situation where we start at 0.2 meters. We're going to go to 0 and then return to positive position values. So at time 0, the position will be at 0.2. It's going to go, slow down. So let's say that takes 1 second, and then return. So it'll be a motion which is kind of like this. Okay, so it started at 0.2. After 1 second, let's say, was at 0. After 1 more second, it was back to 0.2. And then it continued to go on forward. So in that situation, you would have, we're going to do the same basic thing. We're going to plot points. So here I have position, and here I have time. Let's say I have 0, 1 second, 2 seconds, 3 seconds, and we'll just stop there. And let's see, where do we start? Well, at time 0, the position was at x equals 0.2 meters. At time 1, the position was 0. Oh, I need to put my dot there, sorry. So at time 1 second, the position was 0 meters. And at time 2, it was back to 0.2 meters. And then we'll just assume it continued on in some way like that. So let's go ahead and put in some numbers. Let's assume that this is 0, 0.2, and we'll go ahead and let this be something else. I don't know. Let's say 0.4. Doesn't really matter. It's just really to show us things. This is 3, and when I get up here, 0.4 meters. Okay? And let's imagine that we could have made even more data points there. So let's say that I kind of continuously measured things. And what I learned is that the actual path, if I plotted all the points, is like this. Whoa. Well, I apologize. I was shooting for a parabola. Here, I'll tell you what. A a lesson. Draw the line first, and then mark your points. Okay. There's my point. There's my 3 seconds. And then I'll bump my, fudge the graph a little bit to get it up to 4 seconds, or 0.4 meters. Okay, there we go. After a little bit of tweaking, shooting for something which looks roughly like a parabola. All right. Now, let's see. Let's apply, let's try to understand how the average velocity works. And let's go from time 0 to 2 seconds. We won't go all the way to 4 yet. We'll do 0 to 2 seconds. Let's do that. So it started with a position of 0.2 meters, went to 0, and then was back at 0.2. Okay? So first thing I want to do is let's draw the secant line between those 2 points. So maybe if you don't remember, a secant line in mathematics is just a straight line between 2 points. So in this case, my starting point is here, my ending point is here. The secant line is just horizontal, if I can draw that correctly. So the secant line is horizontal. That would mean that the average velocity is 0, because the average velocity is the slope of the secant line. So average velocity is the slope of the secant line. Because it is flat, that would be 0. Or we can go ahead and apply the formula. Over this time interval, delta t is 2 seconds. And so I would say that V average, switch to blue, I think it shows a little bit better. V average equals the change in position over the change in time. Well, that's the final position, 0.2, minus the initial position, 0.2, divided by 2 seconds. That would be 0.2 meters minus 0.2 meters, delta x is 0, over the change in time, which is 2 seconds. And that's just 0. So either using the formula for average velocity or the fact that the average velocity gives you the secant line over an interval, either way, we get 0. So that's nice. It all hangs together. And then, okay, so now we're happy because it all hung together. But what was the point of introducing all these words and vocabulary? Well, the purpose is to describe the world. So is 0 a good way to characterize the motion of this thing as it's going forwards and backwards? Not really. Not really. 0 might be, so the average velocity we found was 0, but the thing was moving. So we need to refine our notion of average velocity, and what we're going to arrive at is the concept of an instantaneous velocity. So the average velocity is the average velocity over an interval. The instantaneous velocity will be the velocity defined at one instant. And you can maybe see how that works. In this case, we're going to say that when the cart is moving to the left, we're going to say that the instantaneous velocity is negative. So it's negative, 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 turns around, positive, 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 when it goes to the right. And so we're going to say that, oh, but it spent just as much time with a negative velocity as it did with a positive velocity, and when you average them, you get 0. That's going to be the idea. So the instantaneous velocity is going to be a slope, but it won't be the slope of a secant line. The instantaneous velocity will be the slope of a line which is tangent to the position graph. So if you were to, I'll draw one here. Let's imagine we wanted to define or figure out the slope or understand the slope, the instantaneous velocity at this moment right here. What we would do is we would sketch in a curve, or a line, which kind of, it's like a tangent line, so that means it's like the dotted line I drew in kisses the graph, kisses this parabola at one point and one point only. Well, we don't care about one point. And then the slope of the line, which just barely kisses the graph at that point, at that moment in time, the slope of that line will be what we call the instantaneous velocity, because it would give us a rate of change of position at that one moment. And if I wanted to do the same thing over here, I'd have to draw in a different tangent line, which kisses the graph at this moment, and I would use the slope of that line to define the instantaneous velocity at this point. So the way you do that, drawing a line, tangent, just barely, kisses the graph, kisses the curve, that's the subject of calculus. We aren't really going to need to do that. One way you can think of it, though, there's a way that you can think of it from the secant line. So I'm going to draw that and show you that in a moment. If you've had calculus, that's great, and that'll just kind of enrich the things that I'm telling you. You don't need calculus to understand anything in this class. So the idea of an instantaneous velocity is as follows. Take a graph of position. Now, I'll go ahead and draw. I'm not going to label the actual numbers here because they don't really matter. It's the idea that's important. So I'm plotting position and time. And what I would do is I would mark 2 points here. Sorry, I really want to mark 3 points, so let's do that. Okay, what I want to do is I'm trying to find, or to understand, the velocity at this moment, at that snap second. How fast is, or what is its velocity in that one moment? I shouldn't say the word fast yet. We'll talk about that in the next video. So what I could do is draw 2 other moments, one before and one after. And what you could imagine is that, well, okay, so I've got one before and one after. I could find the average velocity over this interval. I would do that by drawing a secant line. Oh dear, apologize. Our work is just not good. My secant line, there, okay. So the slope of the red secant line would tell us the average velocity over this interval. Let's go ahead and imagine, we'll just say that this interval has width delta t in the time direction and delta x in the y direction, or sorry, in the vertical direction. And the slope of the average velocity is the slope of the secant line. Okay. Now, look what happens. If you were to imagine there was like a knob that you could control, and you dial it in and you squeeze delta t. So you kind of imagine you have this curve, but you slide these green dots, and you get closer and closer and closer to the point that you're interested in. And you let delta t get smaller and smaller and smaller, so the green dots are really, 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 really close. And what happens is delta t gets small, and so does delta x, because if the green dots are slide along the blue curve, the change in heights are also going to get really small as they get close together. And ultimately, you're going to get 2 points which just infinitesimally kind of straddle the point you care about. And the slope of that secant line, when it's really, really, really close to the point you care about, is in fact going to be indistinguishable from the slope of the tangent line. So, and that's actually how you would do it. In this class, we won't ever do this. I'm just trying to give you the philosophy, the idea behind it. For those of you who have had calculus, hopefully you recognize this as the concept of a limit, this process of shrinking things. And what we're arriving at is something called a derivative. But all I want to say is the instantaneous velocity is the slope of the line tangent to the velocity, sorry, the position versus time graph. So x versus t graph. Okay. And when we talk about the world, we aren't really so interested in the average velocity. I don't care. My car is driven forwards and backwards as I go home, go to work, whatever. I don't care what the average velocity is as I'm driving. What I want to know is, what is the velocity right now? What we really care about in physics is not the average velocity. We care about the instantaneous velocity. And the instantaneous velocity is given by the slope of a line which is tangent to a position versus time graph. Just a line which just kisses the curve at one point. Okay, so the slope of the blue line is the one we really want in physics. And because we don't really use average velocity very much, and I'm really lazy, I'm not going to keep writing V-I-N-S-T, V-I-N-S-T, V-I-N-S-T. Instead, we're just going to call this V for velocity. So if someone talks about velocity, they mean the instantaneous velocity, unless they say average velocity, and then it means what we did last time. So this is the concept of an instantaneous velocity and how it's related to position versus time graphs. Sometimes I like to put this in sort of I guess a bit of a table or something like that. And what I would say is, if I start with position versus time, I use the slope, I get velocity. Okay? We're going to come back and add elements to that, this table. So it'll be really important to understand how you could eyeball or look at a graph of position versus time and determine the velocity. Now, maybe you can't do it exactly from a graph. We'll have algebraic ways to solve equations to get it later. But even if the curve is bendy, you can kind of estimate it, and you can see various things. For example, if the slope is positive, then that means the velocity is positive. The object is moving in the positive direction. It doesn't mean the position is positive, it just means it's moving in the positive direction. If the slope is negative, then that would mean that your velocity is negative, and that would mean that it is moving into in the negative direction. So the position could be positive or negative, but where it's headed would be the negative direction. Okay? So the slope of the position versus time graph determines the instantaneous velocity. All right, thank you. See you next time.